In this presentation, we will be talking about our own ring buffer lock-free executor for ROS2, which is based on Klepsydra's main product, the SDK. My name is Guillermo, and I'm part of the R&D team here at Klepsydra. Klepsydra is based in lock-free programming. This kind of programming is the high-level wrapper of the atomic operations in the processor, in particular the so-called compare and swap or CAS operation. It was invented back in the 70s, but it didn't really become popular until the early 90s when it was implemented in higher level languages, and then it really took off when Java included it in the early 2010s. Lock-free programming consists on attempting repeatedly to write data in a small piece of memory until the data is in a consistent state. This is usually depicted as a plane trying to land in a busy airport. If the runway is busy, it flies away, and then it tries once again until it succeeds. This technique is substantially lighter than the traditional mutex operations because it is just specific to one small piece of memory, as opposed to a mutex, which blocks a big portion of memory. That is why the traditional lock systems are not deterministics, while lock-free systems are more granular and deterministic. It works remarkably more efficiently. The Klepsydra SDK lies between the operating system and the application. It is designed to simplify the implementation of code that collects and acts on data from multiple sources, such as sensor, external communications, and other events. Its goal is to perform operations faster and more reliably than using traditional locking mechanisms. Our own ring buffer is wrapped in what we call the Klepsydra SDK. It is just another library that's installed in the operating system that receives data from multiple sources. It is essentially a memory sharing system. Our ring buffer is enabled for two different approaches to data processing. The first one is the sensor multiplexer, which uses the ring buffer to process the same data multiple times simultaneously. One producer of data, usually large volumes like a camera or a lidar, and multiple consumers. The second one is the event loop, which uses the ring buffer to process, in a single consumer, data coming simultaneously from multiple sources. Producers can publish to the event loop at different rates, completely independent of each other. The ring buffer streamlines all this data and delivers it into a single-threaded consumer. The data flow process has very low latency. These two approaches have two main advantages. First one, very low power consumption, and the second one is a large throughput of processed data. Our first lock-free executor implementation for ROS2 is built on top of the event loop. Every ROS2 publisher, also called advertiser, is connected to a ring buffer producer. The timers are connected as well to the schedulers in the event loop. Lastly, the ROS2 subscribers are connected to the single-threaded consumers. Execution management in functionality is similar to that of ROS2 static single-threaded executors, where all subscriptions are run on the same thread. Implementation, however, is different. Klepsydra uses subscriptions as listeners, and timers are scheduled functions, all of which run on the same thread. Since the timers and subscriptions are single-threaded, there's no need to clone or to lock. Looking into the issues in ROS2, two of them can finally be solved by Klepsydra ROS2 Executor. The first one, the high CPU usage of the default ROS2 Executor. When large volumes of data or high-frequency data is being placed into the ROS2 Executor, the CPU consumption grows very fast. The second is that the ROS2 Executor becomes unstable when large point cloud data is connected to many subscribers. One producer of this kind of data with many subscribers will drop messages without discrimination, with the risk of losing data. Testing scenarios were built for the above-mentioned issues and then validated in a Raspberry Pi 4. 3 executors were examined under these testing scenarios: the static single-threaded, the multi-threaded executor, and Klepsydra's own executor. Throughout these slides, green will represent ROS2 single-threaded executor, red will be ROS2 multi-threading executor, and blue will be Klepsydra's own executor. In the first scenario, the results prove that Klepsydra executor needs substantially less CPU with moderate data rates, no matter the configuration. Importantly, as the number of publishers increases and the data rate gets faster, the difference in CPU consumption becomes considerably large. At a certain point, as you can see on the lower right graph, we can see that only Klepsydra processes all the incoming messages, whereas the other two executors cannot keep up and start losing critical data. As for the second test case, with the introduction of multiple subscribers per publisher, the obtained results were even better. The Klepsydra lock-free executor can process substantially more volumes of data, where the other executors stop processing data. Klepsydra continues until the physical limit of the computer, utilizing all available resources in an optimal manner. Lastly, as a last scenario, we also verified latency for low publishing rates. As we can see, Klepsydra latency is lower than the other alternatives for the same publishing rate. Now, how to make it all work? We provide a factory of executors, which return shared pointers for interfacing. We need to provide some information. The size of the ring buffer. This is because we use static allocation in order to avoid allocating calls during runtime. This can be customized to tune the performance of the application. The factory can either be mapped to an event loop, a data multiplexer, or a series of event loops. We also provide a test version in order to simplify the debugging of the application. This third version runs in a synchronous, single-threaded blocking queue. We are currently improving the multiplexer executor. The goal is to provide a reliable executor for a single large producer of data. It is worth noting that if there are multiple producers of large quantities of data, then multiple multiplexer executors should be used. We have found in our performance testing that we are able to process large quantities of data and reduce power consumption. A possible topology would look like this: a flow of executors connected, sharing data and executing different tasks within it. The first node, a multiplexer executor, would be in charge of collecting data from the camera, both for further processing and for video streaming. The second node collects the camera information and adds the information coming in from the lidar and radar, and all of it is fed to a vision navigation system. Lastly, on the last connected node, the data is further enriched by the navigation sensors, which are fed to the application control loop. To conclude, when should you use Klepsydra's executor? Well, when dealing with large amounts of data, large number of sensors, and large number of publication events running with limited power, limited tolerance to data loss, and want to implement a solution quickly. This concludes our presentation. I hope you find it useful, and please do not hesitate to contact us with any questions or comments. Thank you very much. Have a good day.